Hi everyone, in this video we're going to be looking at some real basics of differentiation, one of the main topics of calculus. So let's get right into it. We have talked about in rates of change topic about this kind of idea of an average rate of change. So looking at one part of a graph, let's say, and then another place later on down the graph and working out the amount of change that goes on between those two. And we've developed an idea about how we can work out the instantaneous rate of change. That is the rate of change happening at an exact instant. So in terms of a graph, if we've got a distance time graph here, then we're talking about speed. The rate of change here is speed, defined as the rate that the distance changes. So we've come up with a formula that looks like this. And that's the definition of the derivative, or the gradient of the curve, or the slope of a tangent, or the rate of change. All of these words are interchangeable. Okay. So here's an example here where we've got the rate of change, the instantaneous rate of change for y equals x squared at a particular point. So rather than going through a laborious process of doing that limiting process, we can use this formula now. In this case here, we know that x is equal to 3. So f of x plus h just becomes f of 3 plus h minus f of x, which is f of 3 divided by h. So we can now substitute into this formula here 3 plus h. Remember, the function here is y equals x squared. So 3 plus h squared minus 3 squared divided by h. With some squaring, expanding, we get down to here. Divide everything by h, and we end up with 6 plus h. Now we can see that as h tends to 0, this thing here tends towards 6. So the slope of the curve at the point x equals 3 is exactly 6. Here's a way of looking at this function in general, and the syllabus specifically mentions kind of understanding this one. So we just start with a general function, y equals, or f of x equals ax to the power of n. So this kind of general power function, and we're using this way here of showing how we get the rule for doing derivatives. So f of x plus h is this function here replacing the x with x plus h. So we've got ax plus h to the power of n, that's this one here, minus f of x is just ax to the n, divided by h. Okay. So we can factorise a out of the top line there when we do this, and leaving us with this step here. Now the next bit is tricky. What we're doing on the next bit is we are going to expand x plus h to the power of n. Now this is the binomial theorem coming in. I know we remember that. The binomial theorem, which helps us to expand things just like this. So it's written out in this next step here. X to the n plus nc1 times x to the n minus 1. So the powers of n are going down by 1 each time as you go along. And you can see the powers of h are going up by 1 each time. The numbers here come from Pascal's triangle. So if we're talking about n equals 4, we could pick out from Pascal's triangle that fifth line down and work out what those numbers were there at the start. Now, when you do that, you'll see that you subtract off x to the power of n, and you've got x to the power of n at the start here. So those two there will cancel out, and you're just left with all of the middle bit divided by h. Now you can see that h is common to all the terms on the top, and we've got an h down the bottom there as well. So if we divide every term by h, we end up with this thing right here. Okay, so the first term, the h disappears. The next one, instead of having h squared, we've just got h. Next one, instead of having h cubed, we've got h squared. And the last one, instead of having h to the n, we've got h to the n minus 1. Okay, remember we're looking as the limit of this thing here as h tends towards 0. So we've still got a as a common factor of all of this, so that's sitting out the front. We've got nc1 times x to the n minus 1, because basically all of this stuff, as h tends towards 0, all of this stuff here will equal 0 because h is multiplied by all of that. So we'll just end up with this bit here. Now NC1, so for example 4C1 is always going to be 4. The number of ways of choosing one object from 4 is always 4. So NC1 is always just going to be n. So that's where we get finally this formula here. And now we've got a formula for finding the derivative, a much quicker way of doing it. So here it is here. If y is ax to the n, then the derivative is a times n x to the n minus 1. So the way I remember this is you put the power down the front and then you subtract 1 off the power. The way that you say this, by the way, is dy by dx. Okay, it's not dy over dx, but dy by dx. Okay, let's do some examples. So in this one here, we've got y equals 3x squared. Dy dx, the derivative is, we bring the number down the front, so 3 times 2 is 6, and subtract 1 from the power. 2 minus 1 is just 1. So you could write 6x to the power of 1, or that's just 6x, so you don't need that power of 1. So that's 6x. Part B, y equals 7x cubed. Now I'm going to be lazy here and write y dash. That's another way you can write the derivative. So bring the number down the front. 3 times 7 is 21, and subtract 1 from the power. 21x squared. C, y equals 2x to the power of 5, so the derivative is 10x to the power of 4. Bring the number down the front, subtract 1 from the power. For D, y equals 3x, that really is 3x to the power of 1. So we bring the number down the front, which gives us 3 times 1, which is 3. We subtract 1 from the power. 1 minus 1 is 0. And we know that anything to the power of 0 is 1. So the derivative here is just 3. Now if we think about D, y equals 3x is a straight line passing through 0, 0 with a gradient of 3. So if I ask you what's the derivative, what's the slope of that graph, it's obviously 3 at every point on that graph. So this answer here, that the derivative is equal to 3 independent of x, makes sense. The derivative is always 3. And the last one, y equals 7. I guess we could write this as 7x to the power of 0. So number down the front, 7 times 0 is 0, subtract 1 from the power, this is just 0. So I guess we can use the rule here, but in either case the derivative is equal to 0. And again, let's think of this in terms of a graph. Y is equal to 7 is a horizontal line passing through y is equal to 7, and you can see at every point on that line the gradient is 0. So again, this answer makes sense, that the gradient at any point on that curve is equal to 0. Second example, determine the gradient of the curve 3x to the 4 at the point 248. Okay, so we want the derivative. So dy dx, the derivative of this function here is number down the front, 3 times 4 is 12, subtract 1 from the power, 12x cubed. Now remember, this function here defines the gradient at every point on the curve. So we're specifically looking for the point when x is equal to 2. It really doesn't matter about what the y value is. We really don't need that information. The important thing is this equation here tells us the slope for every x value. So in this case here, it's 12 times 2 cubed. So we go 12 times 8, 96. That is the slope of the curve when at the exact slope of the curve when x is equal to 2. Example 3, find the coordinates of the points on the curve y equals x cubed where the gradient is 12. Okay, so what is the gradient? The gradient here is number down the front, subtract 1 from the power, 3x squared. That's the gradient of the graph. And the question's saying, when is that gradient equal to 12? So when is that equal to 12? Simple. Divide by 3 gives us that, and x is plus or minus 2. Remember, when we're square rooting both sides, we need to take the positive or negative root. Now we've got our x values, but the question says coordinates. Okay, so we need to find the coordinates of that point. So if y is equal to x cubed, then our two y values are 2 cubed, which is 8, and the other y value is negative 2 cubed, which is negative 8. So our 2 points are going to be 2, 8, and negative 2, negative 8. Okay. Now if we think about the curve of y equals x cubed, it does something like this. Has a stationary point of inflection there at x equals 0. Does something like this. And the question's saying to us, when is the slope of that curve equal to 12? So right there and right there, you can see there's going to be 2 points on the graph. That's going to be 2, 8, and this point down here is going to be negative 2, negative 8. So you can see from the graph that that looks about right. Last one on here, we're going to find the equation of a tangent now for this particular curve at a particular point. This is a pretty simple process as well, because now we've got a way of finding out what the slope of the curve is. So let's do it. The slope of the curve at any point is number down the front. So 3 times 0.5 is 1.5. Subtract 1 from the power. So we get 1.5x squared. So at the point 2, 4, the slope of the curve at that exact point is 1.5 times 2 squared. Remember, we're just looking at the x value here. We're not worried about the y value. The equation tells us it's 1.5 times the x value squared. So 4 times 1.5 is 6. So we've got the slope of the curve at that point. Now that's the exact same as the slope of the tangent. Okay, so to work out the equation of a line, I need 2 bits of information. I need the slope of the line and I need a point on the line. And now I've got both. I've got the slope of the line, I've got a point on a line. So here's the equation of the line. Y equals mx plus c. The y value is 4. The gradient is 6. The x value is 2, and this helps us to work out what c is. 4 is equal to 12 plus c. So c must be negative 8. So therefore, the equation of the tangent is y equals 6x minus 8.